Hello everyone, welcome to the course of ultrasonic testing technology. The main content of this course is the method of locating defects in ultrasonic testing. Through the study of this lesson, I hope to achieve the following teaching objectives. Master the meaning of ultrasonic flaw detection defect location. Master the defect location method of longitudinal wave detection. Master the defect location method of shear wave detection. Plato, the ancient Greek philosopher, once said, "A good beginning is half success." It is very important to position yourself correctly. Only when you clearly recognize yourself and give full play to your potential, success is not far away. From Plato's famous words, it is not difficult for us to find that accurate positioning of ourselves is of great benefit to our life. Then, in industrial production, what is the significance of defect positioning when ultrasonic testing is carried out on workpieces? What is the specific positioning method? Let's study together today. First of all, we need to make clear that the main purpose of ultrasonic testing is to locate and quantify defects in a workpiece. And its significance is to obtain relevant information such as the precise position of defects in the workpiece and the severity of defects so as to provide a basis for the evaluation of workpiece quality. Generally, the basic steps of defect location in ultrasonic testing are as follows. Establish a suitable three-dimension coordinate system on the workpiece to be tested. Adjust the scanning speed, scan the inspected workpiece, detection of defects, measurement, and calculation of defect positions. The establishment method of coordinate system for detect location of common forging and butt welds is shown in the left and right figure respectively. Next, we will learn the defect location method of longitudinal wave straight probe detection. The steps are as follows. As we can see, first, measure the size of the inspected workpiece and establish a three-dimensional coordinate system on the inspected workpiece that is convenient for expressing the defect positioning. According to the thickness of the workpiece to be inspected, select the appropriate longitudinal wave scanning speed of 1 to m. Then calculate the horizontal scale values x1 and x2 of the primary bottom of B1 and the secondary bottom wave B2 on the instrument screen. Adjust the depth fine adjustment and pulse shift to align B1 and B2 with horizontal scales x1 and x2 of the instrument respectively. That is, complete the 1 to n scanning speed adjustment. After detection sensitivity is adjusted, the workpiece is scanned from the 0 point at the left end, and the constant pressure on the probe is maintained during the scanning movement to ensure good coupling. After the defect wave is found, slowly move to the probe in the direction of up, down, left, and right near the defect to find the highest position of the defect wave amplitude. And then we record the horizontal scale value of the defect wave. That is, the defect depth is obtained as we can see. Use a steel ruler to measure the distance between the probe enter and y-axis and x-axis respectively. That is, to obtain the x value and y value of the defect. Finally, the defect position is accurately determined as x, y, z. Next, we will learn the method of detecting and locating defects with a shear wave angle probe. Generally, there are two situations for ultrasonic transverse wave to find defects. One is that ultrasonic waves find defects before reaching the bottom of the workpiece. The method is called direct beam method, also called primary wave method. In the other case, the defect is found after the ultrasonic wave is reflected by the bottom surface once, which is called the primary reflection method, also called the secondary wave method. When the primary wave method is used for flow dictation, the following relationship existing among the parameters in the red triangle in the figure, as we can see here, the formula. Therefore, the actual ultrasonic sound path is equal to the scanning speed ratio times and the horizontal scale value of the reflected echo generated by the defect in the workpiece on the oscillograph screen, as we can see here. The horizontal distance L is equal to the sound path times sine beta, and the defect depth is equal to the sound path is times cosine beta. First, we adjust the 1 to n scanning speeds according to the sound path adjustment method. That is, we need to make the horizontal scale value of the instrument form a 1 to n proportional relationship with the sound path of the actual ultrasonic propagation. At this time, the sound path, as we can see here, is the formula sine, as we can see, and defect depth, as also we can see here. Please remember this. We can calculate the obtained depth h, the horizontal distance L. We can accurately position the defect in the workpiece. Horizontal adjustment method, that is, the horizontal scale value of the instrument and the horizontal distance h, form a 1 to n proportional relationship. At this time, the horizontal distance, as we can see the formula, I hope you can use and learn to it. Depth adjustment method, that is, the horizontal scale value of the instrument and the defect depth h from a 1 to n proportional relationship. At this time, as we can see here, the formula, horizontal distance formula here, and you know the above are 3 cases of defect location using the primary wave method. When the secondary wave is used for flow dictation, the ultrasonic wave first propagates to the bottom surface of the workpiece, and then meets the defect after the primary reflection, forming the defect reflected wave F. At this time, we take the workpiece bottom as the symmetry line to make the image A of defect A and image of the secondary wave path. At this time, we can find that H1 and S form a triangle relationship in the blue triangle shown in the figure, as you can see here. The true depth of the defect is H, and H equal 2T minus H, as we can see here. There is another formula I hope you can remember. Let's take a look at the process of defect positioning based on the second wave method and the sound path adjustment method. First, actual sound path of ultrasonic waves, as we can see this formula, and horizontal distance adjustment method. Horizontal distance formula here is another one. The third one, when using depth adjustment method, this is the third formula. I hope all of our students can learn it and master it. To sum up, it is mainly necessary to determine the depth h and the horizontal distance L of the defect in transverse wave ultrasonic flow detection to accurately locate the defect. In this process, the first thing to be determined is whether the reflected wave of the defect on the oscillograph screen of the instrument is generated by the primary wave or the secondary wave. The specific judgment method is as follows. Assuming that the weld with plate thickness of T is detected. If the scanning speed is adjusted according to the depth for the weld with T plate thickness, then when scanning the weld, the horizontal scale T on the oscillograph screen of the instrument corresponds to 1 time of the plate thickness depth, and the scale of 2T corresponds to 2 times of the plate thickness depth. Therefore, The defective wave generated by the primary wave should appear between the horizontal scale 0 and the scale Tm. And the defect wave generated by the secondary wave should appear between the horizontal scale. As we can see here, we can also use this kind of way. The above shear wave detection method is aimed at the detection method of butt welds on flat plates. However, if cylindrical workpieces are to be detected, the method and the formula are different. So next, let's understand the defect location when we use shear wave circumferential flow detection for the cylindrical workpieces. The detection of cylindrical workpiece is divided into outer circumferential detection and inner circumferential detection. As shown in the figure, in order to accurately determine the position of the defect in the outer circumferential direction, two parameters needed to be determined. One is the depth of the defect from the outer surface, and the other is the arc length from the probe incidence point to the projection position of the defect on the outer circumferential surface. First, we can calculate as this formula shows, and then another formula is the horizontal distance. That is to say, L equals to KH. BO equal BC square under the root CO square is CD dust. So the depth of the defect from the outer circular surface H equal to R minus BO is calculated. From the right triangle BOC, according to the triangle relationship, it can be calculated that angle. Finally, according to the radian formula, as we can see here, that is, the defect position is obtained. Let's look at the inner circumferential deflection of the shear wave. As shown in the figure, two parameters needed to be determined to determine the defect position during inner circumferential inspection. One is the depth of the defect from the inner surface, and the other is the arc length from the probe incidence point to the projection position of the defect on the inner circumferential surface. The specific calculation formula is shown in the figure, as we can see, and the principle is similar to the outer circumferential detection, so I won't repeat it here. Finally, let's understand what factors affect defect localization. First, the influence of the instrument, mainly reflected in the performance of the instrument related to positioning, such as the quality of the horizontal linearity and the accuracy of the horizontal scale of the instrument. The influence of probe, such factors as the defect angle of the main sound beam, the change of K value caused by the wear of the wedge of the angle probe will affect defect positioning results. Influence workpiece, mainly the influence of surface roughness, contact surface shape, boundary effect, and defect orientation. Influence of operations, mainly reflected in the proficiency of operation methods and influence of human errors. Okay, that's all for this lesson. Thank you for watching. See you next time.